Okay, so evening all, welcome to the Additional Science Chemistry Revision Hangout, finally. Again, apologies if you didn't if you weren't able to join earlier. It was all YouTube technical difficulties, hence why this link is under triple physics and not chemistry. But if you've got any questions, please write them on Frog. Again, if you know other people are trying to get on earlier, then please do tell them that the new link is now available. So I'm going to go through, first of all, the fact that for chemistry, just like C1, you have a data sheet. So please make use of it. Make sure that you use the key, because that's really important. It tells you the top number is the mass and the bottom number is the proton number. And you might need these for a couple of questions in relation to your C2 paper. Furthermore, you might also need the reverse of this sheet, which has reactivity series and ions on it. Now these are really important when it comes to electrolysis, because if you can't remember whether the metal ions are positive or negative, you can just come here and have a look. For example, you've got some metal ions here, and that will give you a clue that they are positive, so they will move to the negative electrode. And you also have some ions over here which might help you out for electrolysis or other questions in the exam. So if you are stuck, do have a look at this data sheet to help give you a few clues. So 6 mark questions then, historically, and then we'll go through a bit of the content to give you a little bit of an overview. So 6 mark questions in the past, we've had describe and explain questions in relation to rates of reaction. We've had the structure and properties of bonding. We've had a couple of method questions as well. For chemistry, they do really like method questions. For example, rate of reaction. If you have a look in your revision guide, you'll notice loads of different experiments in relation to rate of reaction. They could give you some equipment, perhaps maybe a conical flask and maybe a gas syringe. And they might say a question like, how would you use this equipment to test for a rate of reaction? Or they might ask you about method for making salts, can be a tricky one, maybe soluble salts or insoluble salts, which we'll talk about later. Perhaps also, if you're talking about method questions, they could ask you about electrolysis, maybe a little bit of electroplating, which we'll discuss later. Maybe how would you set that up and where would the ions move to and things like that. So just bear in mind that for your 6 marker, it could be a method style question or a longer wordy answer. But as always, make sure you write all over the white space, plan your answer before you write it down. Moving on then, we'll talk about the key topics in the C2 paper. So we've got atoms and a little bit of different stuff compared to C1, but we've got all the bonding stuff, okay, covalent bonding, giant covalent and things. We'll talk about new materials and polymers and alloys, chemical reactions and the calculations we've got to do, chemical analysis such as chromatography, gas chromatography and things, and rates of reaction, salts, there's a big topic on salts, and electrolysis. So feel free to post any questions on Frog that you want me to answer, and I'll go through those as I can as well. Okay, so first of all, let's talk about bonding. We have ionic bonding, and these substances are made up of, the clues in the name, ions, so those positive or negatively charged particles, and is something, for example, like sodium chloride, where you have positive sodium attracted to the negative chloride ions. There's a couple of things they'll ask you about bonding. One of them might be, tell me about the structure of the molecule, and the other one might be, tell me about, the compound, or tell me about the properties of the compound. So when you're talking about structure, you need to get the keywords such as that it's a giant structure, that it's a lattice structure, okay, with lots of, lattice just means it's a regular pattern with lots of repeating parts. You also need the idea that it's formed from ionic bonds, and that you've got what we call electrostatic forces holding those ions together. That just means where you've got a plus and a minus, that attraction there we call an electrostatic force. Properties then, you need to more talk about the melting points and the boiling points. So we're talking for ionic substances, the fact they've got a high melting point and a high boiling point. Those two come hand in hand. So that could be 2 marks for writing a very similar thing. And the idea that as a solid, it doesn't conduct electricity. Now this is really important when we talk about electrolysis a bit later, because actually if this was then melted, okay, if we put this up to really high temperature, melted, you would then have a situation where you've got the positive ions and the negative ions being able to then move. And because these charged particles are moving, that is a flow of current. Okay, so these can conduct electricity when they're molten, so when they're a liquid, but they can't conduct electricity when they are just a solid. Because the ions are fixed, they can't move around. Now, linking conducting electricity into metals then, this is a key bit that forms part of the higher paper. If you're doing higher, you need to remember this, that metals conduct heat and electricity because of their, you might see it as delocalized or free electrons. And you'll see, you need to recognize the metals in these two parts. So this just shows here the positive ion, metal ion in the middle, and around the outside, that is where you have the electrons. And they are free to move throughout. So this diagram just shows it as a sea of electrons around the outside, or sea of delocalized electrons, but you also need to bear in mind that it might come in a little bit of a weird diagram like this one here. So this over here is the bonding in metals. We also call that metallic bonding. For example, if you pick up a piece of copper or a piece of gold, for example, all those atoms in that gold are stuck together because they are bonding in this way. So we've done ionic bonding over here. We've looked at metallic bonding. Let's now talk about covalent bonding. Now for covalent bonding, we need to be able to draw the outer shell electrons of covalent molecules. For example, this here, NH3 is ammonia. You need to be able to do this for things like methane, CH4, hydrogen, maybe oxygen as well. So these over here are what we call simple covalent molecules. They are simple molecules and they are bonded covalently, which means they are sharing electrons. So hydrogen is sharing an electron with nitrogen, so it's got a full outer shell, and nitrogen similarly is sharing the electrons with hydrogen, so it has a full outer shell. You can see there's one pair sharing here, here, and here. What you need to bear in mind, though, is you might see them in a couple of different ways in the exam. You might simply see a covalent bond as a line, or you might see it as a dot and circle like this, or with the outer energy shells showing like this. For higher tier, I want to highlight this really important thing, is that substances which are simple molecules have only weak forces of attraction between the molecules. So they have weak intermolecular forces. What that means, if I talk about it in terms of drawing the molecules like this, let's say this was an oxygen molecule, O2, and there was another oxygen molecule over here, and perhaps another one down here. They would have weak intermolecular forces between the molecules. This is a very common question on the higher paper. Okay, you can show them here just by some dashed lines. And all you need to know is that when a substance is boiled to turn from a liquid into a gas, it is these intermolecular forces between the molecules that are overcome, and not this strong covalent bond which actually exists within the molecule. Okay, so bear in mind that for higher paper, I'll just emphasize that down here, is the intermolecular forces that are overcome and not the covalent bonds when these simple things melt or boil. So, for example, it could be liquid water turning into a gas. It's the intermolecular forces that are overcome, not the covalent bonds, because that would split the molecule. So everyone, foundation and higher, needs to know about giant covalent structures. So these are simple molecules, and a lot of covalent molecules are quite simple. They have low melting points and boiling points. You can kind of remember this because most of them are gases at room temperature, like methane and oxygen and hydrogen. So they must have boiled at a really low temperature to be a gas at room temperature. So they've got low boiling points, low melting points, and of course they don't conduct electricity either. So going from the simple then to the giant. So there are a few giant covalent structures. They're quite rare, and we only need to know about ones called diamond, which is shown by this structure here, graphite, which is shown by this structure down here, and also one called silicon dioxide. Now that has a very similar structure to diamond, but it is made up of silicon and oxygen. Okay, so it looks very similar to this one here. So diamond then, this structure all made out of carbon. That's what people forget. Carbon is just a black powdery substance, but when it's arranged in a particular format, it makes diamond, and it also makes graphite. So these two are both made out of carbon, whereas the structure, which I haven't got a picture for, let's assume it would be here, is made out of silicon and oxygen. Now, these giant covalent structures have a high, unlike the simple molecules, they have a high melting point and boiling point. Diamond, because the arrangement of the carbon is particularly strong, and we need to describe their structure. So this is a regular lattice structure. We've got graphite down here, which is in layers. And graphite is special. Again, a higher tier thing that I'm trying to point out for you. For higher tier, you need to know that graphite has one spare electron that can conduct electricity. So if you have a pencil and you sharpen both ends, you've got pencil in your graphite, so your pencil could conduct electricity. So the reason it has that spare electron is because it's made up of carbon, but each carbon only makes 3 other bonds with carbons. And because of that, it's got one spare electron that is not bonding with anything, and that spare electron is then free to move throughout the graphite. Okay, so carbon makes 3 carbon-carbon bonds with other carbon atoms, whereas diamond makes 4 carbon bonds. So each carbon makes 4 bonds. Okay, so giant covalent structures here, you need to remember the names diamond, silicon dioxide, and graphite. These two look very similar in structure, but carbon and graphite are made out of, diamond and graphite are made out of carbon, and you need to remember that graphite has this spare electron so it can conduct electricity. Okay, so lots of stuff on bonding there. If you need any more help on that, feel free to watch my other YouTube videos for more help. Let's move on to electrolysis then, one topic that is a heavy one in the C2 exam. Let's start off first of all with the basic principles of electrolysis. It is splitting stuff up using electricity. And in a very simple setup, you'd have a negative electrode, a positive electrode, so let's put a minus on there and a plus, and we'd have that in a molten, so a liquid substance of the stuff that we want to split up. For example, if we had lead bromide, which is Pb, Br2, we could split that up using electrolysis, and in there we'd have ions of lead, and we'd have bromide ions as well. Okay, so lead ions and bromide ions. And quite simply, opposites attract. So the negatively charged ion would move to the positive charged electrode, and the positively charged ion would move to the negatively charged electrode. Okay, so we could do lead bromide, or similarly you could have something like zinc chloride, or any kind of molten ionic substance that you want to split up. So in the same case, if you had the chloride is negative, so that would go to the positive electrode, and the zinc is positive, so that would go to the negative electrode. But that's the simple principle of it. And we need to be able to complete for high tier only, so if your foundation, just switch off just a sec, but higher tier you need to calculate half equations for what's happening at the electrodes. So if we think about what's happening at the electrode, anything that's positive wants to gain electrons. Okay, so the lead ion here, to turn back into lead, it wants to gain electrons at that electrode. Whereas the bromide ion wants to give away its extra electron that it's got to become bromine again. Now, just to go through for the higher tier, if you are lead, for example, you want to gain 2 electrons to become a lead atom. So you would gain 2 electrons and turn into lead. Okay, so that's how we would write the half equation for what's happening at this electrode. The difficult one comes in with these negative ions, because you need to remember that most of these make what we call diatomic molecules that go around in 2s. So bromine, chlorine, oxygen. Okay, so anything like that coming off is always going to make O2, not just O, okay, not just Cl, not just Br, they go round in pairs. So this is why down here, if the example was chlorine, you'd have chlorine giving away 2 electrons and becoming Cl2-. So this one's balanced, you need to make sure they're balanced. Or you can write it in this way, that chlorine turns into Cl2 and 2 electrons are given off. So just to do the one in our example, we've got bromine, Br-, that would give away 2 electrons, so it turn into bromine, Br2, and you'd have electrons free. But just because we got this Br2, because we said up here always makes bromine, we need to balance it. So 2 Br- and 2 electrons there. So back to what everyone needs to know. Oil rig, okay? Oxidation is loss and reduction is gaining of electrons. Okay, so with oxidation is losing electrons, reduction is gaining electrons. So we just need to look here and see whether oxidation is happening at this electrode or whether reduction is happening at this electrode. So we said here the lead ions are gaining electrons, so reduction is happening over here. And on this one we say that the bromide ions are giving away electrons, so oxidation is happening over here. So if you remember that oil rig and write it down, oxidation is losing electrons, reduction is gaining electrons. That will help you remember where oxidation and reduction are happening. So quick question, how many marks are the half equations? There'll probably be 1 or 2 marks. They'll have half of it or probably already there for you, and you would have to complete it for 1 mark and balance it for the other mark. A question says, unless an exam question says the electrolyte is molten, should we assume that it's dissolved in water? They will make that clear for you in the exam, and we'll come on to the different types of electrolysis in just a second as well. So in this case, they'll say that lead bromide, or they'll give you the picture of the ions, and you'll know that there's nothing else in there, it's not in solution. But over here, let's talk about a couple of different forms of electrolysis then. So they take those basic principles of opposites attract, positive things to go to the negative electrode, negative things to the positive electrode. And let's look at our examples. First of all, I want to talk about electroplating. I said they could have a method question about setting this up. Okay, they might not, but it might come up there somewhere. With electroplating, you want to cover a particular object with a particular metal. So, for example, in this case, let's say we wanted this to be a silver-coated spoon. And you'd set up your electrolysis with your metal that you want the spoon coated in, your spoon, and your electrolyte, as we call it, around the outside. So here it's giving you a clue that's a solution, okay, because it's got aqueous. But you've got your electrolyte around the outside. And what you want then is this to be on the negative electrode, because silver ions are a metal, so silver ions are positive, as you can see here. This says Ag+, and the silver ions will move from this electrode to there. Similarly, they might move out of the solution, AgNO3 is what they're in, onto the spoon, and you'll end up with silver coating the spoon. So they might have a setup in the past. They've had questions where they've had this setup wrong, with the spoon at the wrong place. Remember, the spoon needs to be at the negative electrode because that's where you want these silver ions to move to. Similarly, the electrolyte that is in must contain silver. So here we've got AgNO3, silver nitrate, silver nitrate. It can't contain, for example, copper sulfate, because if it did, you could have the copper moving to the spoon and you'll have a mixture of copper and silver on the spoon. So you can't have that. It must contain the same ions that you want coating in the spoon. Another example of electrolysis then, which makes everything a little bit more tricky, is this one, the electrolysis of aluminium oxide. The tricky thing about it is you've not got your usual one negative electrode, one positive electrode, okay? Everything's a little bit more complicated than that. You have positive electrodes, and there might not be 3, there might be several. You might get a diagram where there's 6 or 7 electrodes in there. But you get your positive electrodes, and they are made out of carbon. And along the outside and along the bottom, weirdly, is your negative electrodes. And all of that is negative. So if you wanted your aluminium oxide to be separated, you'd get your ore and melt it down so it's molten. And in here you would have aluminium ions, which would be positive, Al3+, and you would have your O2- ions as well in solution. So because the aluminium ions are positive, Al3+, they will of course move to the negative electrode, and you end up with aluminium at the bottom, which, because it's all hot in there, it will stay liquid, and then you can take it off and get out your aluminium. The other thing that's in there is the oxygen. So because an oxide ion is negative, that will go to the positive electrode, and that will be attracted here. Now, you could get oxygen given off, but because these are made out of carbon, what happens is the oxygen reacts with the carbon, and you end up actually with CO2 coming off. Okay, this is why the carbon anodes here, or the positive electrodes, needs to be replaced. So that comes up commonly. Why do these need to be replaced? And it's because the oxygen reacts with the carbon and produces the carbon dioxide, which gradually wears them away. If we were to take then the rock, aluminium oxide, that ore, and melt it down, it would be really expensive. It would cost loads of money in terms of energy and electricity to heat that up and separate it. So one trick that we've got, which you need to know for your exam, is that we've got something called cryolite. And what happens is we add cryolite to this molten aluminium, mix the aluminium oxide with cryolite, and what it does is reduces the energy needed for the electrolysis. So this lowers the melting point and reduces the energy needed for electrolysis. So it reduces energy and reduces money needed for the electrolysis. If you didn't have it, you'd have to heat this up to a really high temperature for the electrolysis to happen. But with that cryolite, it makes everything affordable. Your final one then for electrolysis is the electrolysis of salt water, otherwise known as brine, like you keep hot dogs in. Now, this is where things get a little bit more confusing. Salt is NaCl. Okay, sodium chloride is our standard table salt that we use in the home. And water is obviously H2O. But when they are mixed together in an aqueous solution, so when the salt is dissolved in the water, you end up with a situation where you've got a tank with sodium ions in, chloride ions, H+, hydrogen ions, and OH-. You can see here that the Na and the Cl are split up, and for water, you have hydrogen and hydroxide ions. Now, if we were to stick the electrodes in here, positive and negative, you would have a difficulty thinking about which ions would move where, because you have two things that are positive and two things that are negative. So what actually happens is at the negative electrode, you end up with the less reactive thing going there. So hydrogen moves to the negative electrode and it will make hydrogen, and you can use that to make hydrochloric acid or in the Haber process or something like that. Chloride ions over here go to the positive electrode and you'll end up with chlorine gas coming off, and you can use that as a disinfectant or to use in swimming pools and cleaning products and things like that, or again to make hydrochloric acid maybe. And left in solution then, you end up with the sodium bonding with the hydroxide to make sodium hydroxide, and that can be a really useful product to use in soaps and things like that in soap industry. So difficult one here when you've got lots of ions. The less reactive ion will move to the negative electrode here, which means because sodium's more reactive, it will bond straight away with that hydroxide and stay in solution. So quite a big topic, electrolysis. Use the ions on your data sheet to help you think about which electrode things are moving to. You'll get aluminium on there, you'll get oxide on there, you'll get silver ions on there and sodium. So do use that data sheet to help you out. Moving on then to rates of reaction and talking about things colliding together. So let's talk about why reactions happen in the first place. Well, let's draw a couple of particles here that can react with each other. Now those particles, just by the fact that they're moving anyway, will maybe collide with each other. Okay, but they won't necessarily react. They might just bump into each other. They only react if they have enough energy. We call that energy the activation energy. So only would a reaction happen if the particles have the activation energy. And there's a few things that we can do to increase the rate or the speed at which the reactions happen. For example, we could increase the concentration, increase the pressure, increase the temperature, or increase the surface area. With relation to surface area, that basically means if you had one big cube and chopped it up into a powder, this powder would have a much larger surface area than the cube itself that started off with. There's much more surface on that powder that the reactants can bash into and collide with. Now, the key thing with this rate of reaction and collisions comes under the title collision theory. Now, they might use that in the exam because they have used kinetic theory for physics and stuff before, so they may well put in that term collision theory. All it means, the clue's in the name, is talking about particles colliding with each other. Because if you increase the concentration or the pressure or the temperature or the area, you are increasing the frequency of collisions, or even better to put, successful collisions, because they're colliding anyway. So you're increasing the frequency of successful collisions, and that is going to increase your rate of reaction. So it's very important to get either the word collide or collisions in your answer when you are talking about rate of reaction and changing one of these things. That's a really, really important key word. With temperature, there might be a couple of other keywords we put in. For example, if we increase the temperature, actually our particles are moving faster. And one extra little thing is that more of them have the activation energy, because you're actually, with temperature, you're giving the particles more energy, they're moving faster, and more particles have the activation energy. So whenever you think about rates of reaction, you need to think about collisions or colliding particles and particles moving fast and having the activation energy for the reaction to actually happen. They may well ask you a method question in relation to measuring the rate of reaction. So for example, like I said before, it could be to tell how quickly reaction's happening. It might be how long it takes to produce a certain amount of gas in a syringe. It could be looking at the change in mass. So if you had your equipment on a balance, for example, which is going to read your read your mass, it could be how quickly does the mass change, because mass may be lost as a gas out of the top, and that will give you an indication of how quickly the reaction is happening. So lots to talk about rates of reaction, but only a few key words to get in there. Collisions, activation energy, and if you're talking about temperature, the idea that the particles are moving faster. So moving on, we're going to talk about analysing substances. Again, feel free to write any questions on frog as we go through. There's a couple of questions on mould and yield, and I'll come back to those a little bit later on, but feel free to ask anything else as you go through. When we're talking about analysing substances, we've got paper chromatography and gas chromatography. Now, paper chromatography, first of all, can be used to separate things like maybe food dyes or additives or something in foods. And with this, you would put your food dye on a pencil line at the bottom. You don't want to put it on a pen line, otherwise that will smudge and run up. You would have your known component that you want to look for. For example, if you wanted to look for a band food dye X, you would have a look at the pattern that X would give as it was drawn out of the paper and compare it to your other foods. Maybe let's call those 1 and 2. So if you wanted to know whether foods 1 and 2 had this banned substance X in, you could put a little mark of all of them at the bottom of your paper on the pencil line, dip it in water or in a solvent which will dissolve these particles, and they will travel up the paper. And those ones that move quickest will be at the top of the paper. And it's basically a way of separating a substance. And then you'd compare it to X and have a look at the patterns to see if they are similar. On the other hand, you can use gas chromatography. Now this is a machine, but unfortunately in the exam they didn't use the word machine. They try and complicate things by using the word instrumental methods. I basically want you to think about these as machines. Okay, and there's 3 advantages of using instrumental methods over other methods, which are the fact that they are fast, they are sensitive, which means you only need a small amount of the substance, and they are accurate. Now they could well link in gas chromatography, something's happened in the news, for example the Euros or the Olympics or something like that, because this is the type of machine that might be able to separate a blood sample or a urine sample, for example. So let's suggest it was urine. An athlete wanted to, someone wanted to see whether an athlete had a banned substance in their urine or banned drugs. They would put their urine and probably vaporize it, turn it into a gas, on this injection port here. And a carrier gas, so something inert, something unreactive like nitrogen, would be used to push that urine sample through the column. And then quite simply, it's detected on a recorder. Now this column is normally solid, but that gas kind of just pushes it through, and you can imagine different sized particles and different shaped particles will interact in a different way here, and therefore take longer times to get through. And how long it takes to get through is called the retention time. And you can see that recorded on your monitor as you come out. And you'll get these spikes where different size particles are coming out. So for example, here we can count the spikes, 1, 2, and that will tell us that there are 2 substances in that sample of urine. Now at this stage, this is an important bit because they focus on this in the exam. In this stage for gas chromatography, it is still only separating the substances. Now to actually identify them, this tends to come up more in the higher paper, to identify what the substance is, you link that to a mass, spectrometer, and we call this machine sometimes a GC-MS, gas chromatography mass spectrometry machine. And this will help you identify the actual substance that's in there. So these are 2 separating techniques to separate the samples. And you need to remember, they could talk about this in a 6 marker maybe, comparison of them, how they work. And you need to remember that machines or instrumental methods are faster, more accurate, and more sensitive. Okay, we're getting good for time, so we'll keep on going through, probably be even about another 10 or 15 minutes, and then we would have finished the C2. So moving on, we will talk about new materials, really hot topic. You've got polymers. These ones with the cross links are your thermo setting polymers. You need to recognise these as cross links. You'll also get polymers like this without cross links, which might be described as thermo softening. The clue's in the name here, thermo softening. You're softened by heat. Okay. You might also see something called a low density polymer or a high density polymer. They'll give you the information you need in the question, but high density means that all the chains can be squashed together really easily. But at low density, they're all branched off from each other. So it's really difficult to squash them all together and make them really dense. So it's the low density ones that have the branches. They might also talk about nanoparticles, easy marks if they do, because you just need to describe a nanoparticle as a very small particle. If you don't put that very there, you won't get the mark. It has to be very small. And they are in the size of 1 to 100 nanometers. You need to remember that range, probably a multiple choice for that one, but 1 to 100 nanometers. And they make good catalysts because they've got a big surface area for particles to come on and react, okay, because they've got a big surface area to volume ratio. So you can imagine this, if this was put in a reaction, you've got loads of space for those reactants to come together. Because they've got this big surface area to volume ratio, they also used in things like suntan and deodorants. And this is what's helped these products go from something that can leave white stains on your clothes from the big particles. The fact that they're now using tiny, tiny particles, these nanoparticles, means that you don't get those white stains on your skin from suntan or on your clothes from deodorant. Alloys then. Alloys, you get this a little bit in the C1 as well, so it's probably familiar to you. Normally in a metal, the layers are regular, so they can slide over each other. With alloys, there's a couple of different size atoms because it's a mixture, and that means the layers can't slide easily. So these are a lot stronger. But you've also got something in C2 called smart alloys as well. So as well as the regular alloys that we think of, we've also got smart alloys. Like nitinol used in braces, they are ones that you can bend and heat up, and then they will return to their original shape. So for example, you might make a perfect set of braces for someone's teeth, but then when you put them on their teeth, they might have to be bent around their crooked teeth. But due to the heat of the mouth, that will hopefully force those teeth back into this shape, because it's forcing the metal back into that shape. So lots of things on new materials that could come up. Next then, salts. And feel free, if you've had a bit of chemistry overload because I started a bit late, feel free to stop this and watch it later if you want to as well. You're more than welcome to do that if you want to do so. You've got a little bit of time for your exam tomorrow. Naming salts then, we need to remember that sulfuric acid makes sulfates, nitric acid makes nitrates, and hydrochloric acid makes chlorides. So for example, if we're finishing off these equations, we've got potassium hydroxide plus hydrochloric acid, that would make potassium chloride plus water. So it's a neutralization reaction, an acid plus a base making a salt plus water. In this occasion, we've got magnesium oxide plus sulfuric acid. So because sulfuric acid makes sulfates, we'd end up with magnesium sulfate plus water. Now for the bottom one, when you just have a metal and an acid, you make the salt still, so magnesium nitrate in this case, but rather than water, you make just the hydrogen gas. So if you put just a lump of metal in acid, it will fizz and make a gas, and that is hydrogen. Now if you forget these, it's actually easier to write it out in the symbols, because if you remember, and especially for higher tier, you'll need to remember that this is HNO3 for nitric acid, HNO3, sorry. So Mg and HNO3, you can see that when you make magnesium nitrate, which is actually NO3 2, you don't have any extra oxygens to use. So you can only make plus hydrogen. You don't have any of that oxygen left. So sometimes if you're struggling to work out what gas to make, if you look here, you've used that up, so you've only got hydrogen left. The other one that you need to be familiar with is ammonium nitrate. We said before that ammonia with an A is NH3, but ammonium is NH4, and this should be on your data sheet to remind you. NH3, ammonia, added to nitric acid will give us ammonium nitrate, NH4, NH3, NO3, which is useful as a fertilizer. Okay, so bear in mind that ammonium nitrate, I remember it that ammonium is longer, so it has more hydrogens. Ammonia is shorter, so it's only got 3. So you'll need to be able to finish these kind of equations to name salts, and also we need to be able to make and separate salts. So we'll move on to that just now. So in making salts, they can either be soluble or insoluble, and this is something that people find a little bit tricky, so I'll give you a couple of tricks to help you out. Soluble means it will dissolve in water. Insoluble is the opposite. They don't dissolve in water. So with a soluble one, if you had a beaker of water, you wouldn't know that there was a salt in there because it would all be dissolved in. But with an insoluble salt, if you had a beaker of water, inside you would see that precipitate, that solid salt. Clues to look out for then: a soluble salt would have the state symbol next to it, AQ, because that means it's dissolved in water. An insoluble salt would have the state symbol S to show that it was solid in water. When separating these salts then, for soluble salt, because it's dissolved in water, you would have to do a process called crystallization. And in this process, you have an evaporating dish, you have your solution in here, and you would heat that up over a Bunsen flame until the liquid evaporates, and you are left with your salt crystals. Sometimes, again, in the question, they'll give you a clue. They'll say, for example, copper sulfate crystals are made. That's a hint. First of all, to the fact that you're using crystallization to separate them, and also then to the fact that they must be a soluble salt. On the other hand, if your salt is insoluble and it is like this, suspended in the water, we call this solid stuff a precipitate. And to get rid of the water and separate that precipitate, you would have to filter it. So you'd have yourself a conical flask, a filter, and some filter paper, and you would pour in your insoluble salt, which would collect here, and you'd have the liquid at the bottom. So filtration to separate something that doesn't dissolve in water, and crystallization for something that does. Now, the difficult thing with salts is thinking about when you've actually made your salt in the first place. So before you do the separation, when you've made it in the first place, thinking about how you make it. So what acid are you reacting with to make that salt? And this kind of question, have they used an insoluble base or an alkali to make their salt? Because what you might be asked about is how to make the salt in the process, in a process, for example, actually adding the acid to the alkali to make your salt plus water. They might ask you about this step as well. So the fact you need to know that to make a salt, you might react an acid with an alkali, or just a metal with an acid maybe on its own to make that salt. And I'm not going to go through it now, but I'm happy to go through it a bit later if you want. But you need to think about whether the whether what you're reacting with the acid is a soluble salt in the first place, an alkali, or whether you're reacting with an insoluble base, because you have to do one extra step when you react it with an insoluble base. But I'm not going to cover that now because that's not suitable for everyone. But just bear that in mind and maybe read up on that bit if it's not making sense to you now. So just a couple of calculations, and then that is everything you did for the foundation. And I'm just going to go through empirical formula afterwards for higher tier as well. So a couple of calculations you'll need for the foundation paper and the higher paper is to calculate relative formula mass, which we write as MR. So for example, in this question here, calculate the relative formula mass of this sodium hydrogen carbonate, NaHCO3. They also, in this question, are nice enough for you not to look at the periodic table. They give you the masses as well. All you do here is add everything up. So you add the mass of one hydrogen atom with the mass of, you add the mass of one sodium atom with the mass of one hydrogen atom with the mass of one carbon atom with the mass of 3 oxygen atoms, because that's got number 3 there. So it would be 23 plus 1 plus 12 plus 3 times 16. And you'll end up with a relative formula mass of 84. So that's simply looking how many atoms of each thing have you got and adding up the masses. Percentage mass then is just saying, well, now you've worked that out. Normally it's only 1 mark, look, so it's just going to be a simple question afterwards. It just says, well, now you work that out. What's the percentage of carbon in there? So you simply do little number divided by big number. So you do carbon, which is 12, divided by the mass of everything, 84, times by 100. Okay, so here we've got carbon with a mass of 12, which I'm just dragging down here, divided by the total mass, and you end up with the fact that there is 14.29% carbon in that compound. So very well done. If you kept up with that, feel free to go over not only the stuff that I've just gone through, but also the stuff before, which I've done on YouTube, and you'll see all my YouTube videos. If this is something you're not sure of and you want to go in a bit more detail, maybe electrolysis or making salts or whatever it is, feel free to watch those YouTube videos to help you out. Thank you to Mr. Crowley for letting me use his YouTube, as my one wasn't working. And again, apologies for those of you who were waiting around at the beginning. Okay, it was totally out of my control, but hopefully that was still useful for you anyway. And if there's anything else you want covering, then feel free to come and see us in the science department and we can help you out a little bit more. So stay on for a couple more things if you're doing higher. and then we'll take a break and I'll go through a couple of C3 things. So for higher tier, I want to go through empirical formula. So for example, in here, we say an oxide of lead that does not have the formula PbO contains 6.21 grams of lead and 0.72 grams of oxygen. Calculate the empirical formula of lead oxide. And here are the relative atomic masses they've given you already. And this one, look, it says you must show your working. So don't guess it. You have to show your working to get full marks. Now with empirical formula, you just need to remember to divide by RAM. Okay, so that's a sheep. Remember that's RAM. Okay, RAM, another word for sheep. And for empirical formula, you just need to divide by the RAM. So for example, here we've got lead. It's got 6.21, and that's going to be divided by 207 from up here. And then for oxygen, we've got 0.72, and we divide that by 16 from here. So once we've divided those by our relative atomic mass, all we need to do then is look at the ratio that they give. So this is 0.03 to 0.045. Okay, so if you have that kind of ratio, what you can do is try to simplify that. Now, some of you may already be able to see the ratio in whole numbers here. We have to get these up to whole numbers. But what you might want to do is divide both sides by 0.03 to help you out. So if we divide both sides by the smallest one, we end up with a ratio of 1 to 1.5. Now, those numbers are a little bit easier. We're not quite there because we need this in a whole number. But if we double both, we'll end up with a ratio of 2 to 3. And then all we need to do is write our elements back in. So it would be Pb2O3. Okay, and that would be our empirical formula for those given. Now, bear in mind, you might see this as a percentage. Don't worry about it. Just ignore it. You might see this as ton. Just ignore it, okay? Do not worry about what units this is in. As you can see, they don't play a part in the equation. All you need to do, divide by RAM and then simplify the ratio so that it's a whole number. So that is your empirical formula, an extra thing that happens on the higher tier paper. And either they have an empirical formula, or going back to a question that I've had on Frog, they will have a question on calculating mass or the yield. So this is can be a mass calculation, or you might sometimes see it as maybe these can be also used to calculate the theoretical yield of a substance. Okay, how much theoretically could you gain? That's all theoretical yield means. But in this question, it's saying a company made magnesium using this reaction. So it's had silicon and magnesium oxide making silicon dioxide plus magnesium, and they've balanced it for you 2 to 2. Now what you need to do for this one is think to yourself, well, what have they given me? So they've said I've got 2 MgO. Let's talk about the bits that we need, making magnesium. And their question is saying, well, how much magnesium oxide do I need to make 1.2 tons of magnesium? Again, ignore the units. It doesn't matter what the units say. It could be 1.2 anything. But calculate the mass of magnesium oxide needed to produce 1.2 tons. Now, the rest of the equation doesn't matter. We're not interested in that. We're just interested in the bits that they've given us. So we can cross those bits out. We don't care. But we can't just work out. We can't just guess how much of that makes that. So what we can do instead is think about, well, they've given us some information on relative atomic masses. So maybe that's a hint. I can use those. And what you do is you work out the relative atomic mass of everything on this side. So 2 times by MgO. And you would end up with 80. Okay, because 2 times 24 added to 2 times 16 is 80. And those 80 tons would make 48. 2 times 24. So we've got a situation where we know how much 80 tons would make. 80 tons would make 48, but we don't know how much would weigh 1.2 tons? So if you divide both sides by 48, you can work out how much you would make to make 1 ton. So if you do 80 divided by 48, you would end up with 1.6 recurring. So we know that 1.6 tons of magnesium oxide would make 1 ton of magnesium. Now the final step is to multiply this, I'll do it below, by 1.2, because we want to know not not how much makes 1, but how much makes 1.2. So if you multiply both sides by 1.2, you can then work out how much is needed to make 1.2. So the answer would be 2. So 2 tons of magnesium oxide is needed to make 1.2 tons of magnesium. And they've given our answer there. Look, we don't have to worry about the units at all. They tend to talk about really big units like tons because they're talking about it on an industrial scale. Okay, so that is the extra calculation. They tend to, in the exam, either do a mass calculation or they will do an empirical formula. They tend not to give you both. So just bear that in mind. They might do, but they tend not to. Where it's in theoretical yield, you might see the question written as how much magnesium could we make from a certain amount of magnesium oxide. So it could be switched around the other way. How much of this can we make from a given value, say 25 tons of this? So it could be either way around that they ask you that question. So in relation to yield, I'm just going to go on to that question that I was asked about yield. In a scientific calculation, if you have a look at the relative formula masses, you can work out what is the maximum amount that you can make. So given that you have, for example, 25 tons of magnesium oxide, what is the maximum amount that theoretically you could make from that reaction? And you can work that out in a similar way that we have just done over here. And that would be our theoretical yield. So let's assume, for argument's sake, without working it out, we can assume that this, for example, would give us about 18 tons. Okay, I'm not working it out, but I'm just going to assume that that will give us 18 tons. So if it did, that was to be the maximum amount that we could get. But let's say, for example, that when we measure it, we only get 17.5 tons out. Okay, so we're a bit upset. We wanted 18 because that's what our chemistry told us we would get, but we only get 17.5 tons out. So we're not going to be happy with that. But that is our actual yield. That might be the actual yield that we get out. And this is our theoretical yield. And then quite simply, if our actual yield that we had was 17.5 tons, if our actual yield was 17.5, but our theoretical yield was 18, we could from that work out the percentage yield. What did we actually get as a percent? By doing our actual divided by theoretical and multiplied by 100. So in this case, rather than getting 100% yield out, which we'll never do, we would get 17.5 divided by 18, which would give us a 97% yield. So your yield will never be 100%, okay, because some of the mass might be lost, or the reaction, something might have happened in the reaction other than you were expecting. Okay, so that is in relation to yield and percentage yield. Now, the other question that I was given was on moles. Basically, moles, in the simplest way that you need to know for exam, is that when you've worked out the relative formula mass of something, okay, so for example, our magnesium oxide, okay, when we worked that out, the relative formula mass of magnesium oxide on its own would be 24 plus 16, which is 40. If we put that in grams, 40 grams would be 1 mole. So a mole is the equivalent to your relative formula mass in grams. Okay, if you remember that bit in the exam, any mole question that comes up, you will be able to work out from that bit of knowledge that your MR in grams is 1 mole. Okay, I think that's it for the C2. I am going to take a short break, but I'm going to stay on this video because I'm having technical difficulties with my other links, which are out of my control. So if you want some C2 stuff, then feel free to take a short break and then come back, and we'll continue on this video with some C3 triple content. But that is all for the C2. Again, if you need any more help, I've got lots more revision videos on my YouTube site, or feel free to come up and see me in the morning tomorrow.